There we go. Okay. So we've done simplifying trig expressions. We've used trig identities, all that good stuff. Now we're going to start solving trig equations. And so some of these trig equations will be very basic and simple. And then we'll kind of step through into more difficult ones that require us to do things like we did in the last unit, like factoring, or even just taking out the greatest common factor, stuff like that, within solving a trig equation. So with that, go ahead and grab your notes and we'll get started. That's geometry. Here we go. This is 5.3. Solving trig equations. Okay. So solving trig equations, the first one we're going to do is going to look pretty simple. And a lot of this is going to involve having a pretty good command of the unit circle. So if you're not super strong on the unit circle, I would recommend having a unit circle either in your notes or up on your screen at the same time as doing these questions. And you really should try to memorize at least the first quadrant of the unit circle, because then you can kind of copy it into the other quadrants mentally. Because that's going to make your life a lot easier down the road. It's going to make these problems a lot quicker. And it's going to help you as you go towards things like calculus as well. So solving trig equations, a lot of this is just best done through looking at examples of how you would solve them. So starting with the first one. And the first one's going to be one of our easier ones. Sine of theta equals 1/2. And for this one, we're going to be given a range of values, -pi/2 to pi/2. So sometimes on these trig equations, you'll be given a range of values that they would like you to find all of the solutions within that range. Since these are cyclical, you will, if you aren't given a range, you'd end up with like an infinite amount of solutions. And so in a lot of cases, you'll be given a range of values where your solution needs to reside. But sometimes you'll be given just find all of the general solutions, which is what we'll talk a bit more about tomorrow, because then you'll have to learn how to index them. Kind of like we did with the equation of asymptotes when we were graphing tangent. That was kind of an index of where all the asymptotes are located. You can do something similar with solutions to trig equations. But for now, we're just going to find specific solutions within a range. Okay. So for sine of theta equals 1/2, this is something that in geometry, what you would do to solve it is type sine inverse into the calculator and you would get your answer. Which you can do, but when you try to find things like, or the calculator doesn't tend to spit out answers that are in exact form, like pi/6 or pi/2 or pi/4 or whatever. So when we're doing this in this class, this is where you might want to have a good grasp of the unit circle here. So right away, looking at this one, we want to start thinking about the unit circle. And thinking, where is sine 1/2? Where is the y value 1/2? Because cosine is x and sine is y. So if we think about where theta is pi/6, that's where we have the coordinate √3/2, 1/2. So that is one place within the range -pi/2 to pi/2 where the y value is 1/2. And actually that's the only place, because if you think about -pi/2, that's down here, to pi/2, this is the range we're looking in. This is the only value within that range where the y value is 1/2. You might have a y value of -1/2 down here, but that's not what we're solving for. So the only solution within this range for this equation is pi over 6. So for our answer, we would write theta equals pi over 6. Or if you were given the range of values from 0 to 2 pi, this is one of the most common ranges of values that you'll get, basically the whole unit circle. Then we might have more solutions because all the y values in the top half of the circle are positive. So we're going to hit a y value of 1/2 again, right over here, at the corresponding value on the opposite side of the circle, at 5 pi over 6, at -√3/2, positive 1/2. So for this range of values, we would have two different answers. Theta is equal to pi over 6 and 5 pi over 6. That's the other reason that just typing in sine inverse of 1/2 into the calculator isn't going to always work out, because then it's not going to yield the second solution. It's only going to give you the first one. So that's another reason that we want to make sure we've got a good handle on the unit circle. But anyway, any questions with that first one? Any numbers we're not sure where they came from or anything like that? Okay, so that's a fairly simple type of problem. The next one, we're going to step it up just a little bit. This one, we've got 3 tangent squared theta equals 1. Okay, so for this one, as always, we're trying to get theta by itself. And so in order to get theta by itself, just like we would if we were solving for x or for whatever, algebraically, we have to start doing things like dividing on both sides and square rooting both sides. And on some of these problems, you'll end up adding or subtracting things from both sides. So all those algebra rules still apply. We just have trig expressions now involved. So for this one, the first thing I would do, we also need our range of values here. This one is from 0 to 2 pi. For this one, I would start by just dividing by 3 on both sides. So we get tangent squared equals 1/3. Then we can take the square root on both sides. So we just get tangent equals the square root of 1 is 1, the square root of 3 is, we're just going to leave it as the square root of 3. Oops, forgot to put theta. Okay, so we have tangent of theta equals 1 over the square root of 3, or actually plus or minus 1 over the square root of 3, because when you square root both sides, you end up with positive or negative of the solution. Can't forget that. Okay, so now we have plus or minus 1 over the square root of 3. And notice there is a square root in the denominator, which is not something we typically want. So if we wanted to rationalize this, we would multiply by the square root of 3 over the square root of 3, and we would get plus or minus root 3 over 3. So that's what tangent of theta is equal to. Now we got to figure out what theta is, and that's where we move to the unit circle. And figuring out tangent from the unit circle, unless you have all of the tangent values around the circle memorized, can be kind of difficult. Or not too difficult, just a little bit of, I guess, extra work involved in it. Because we know that tangent is sine over cosine. And if sine is y and cosine is x, that just means the y value over the x value. And we have done this before with going through and finding all of the tangent values around the unit circle. But if it's not something that you have like ready to roll in your brain, that's okay. You can find it using the x and y values around the circle. So since we know that there's a square root of 3 in it, we don't really have to look for in places where there's not a square root of 3 involved at all in either coordinate. So I would start searching at the at pi over 6. Because we have root 3 over 2 and 1/2. So if I'm doing y over x to find tangent, we have 1/2 over root 3 over 2. And for dividing fractions, you flip and multiply. So this is 1/2 times 2 over root 3, which gives us 1 over root 3 because the 2's cross cancel. So this is a solution because 1 over root 3, or you can also rationalize this to root 3 over 3, is one of the things we're looking for here. So pi over 6 is one solution. And keep in mind we're looking for positive or negative root 3 over 3. So we're actually going to get 4 solutions here for this one. So there's one of them. The other one is going to be immediately across the circle if you continue this line. Y over x is also the slope of this line. And so if I just continue this line back, it's going to have the same slope or the same tangent value. So at, let's see, that would be 7 pi over 6. We're also going to have that same tangent value. This is just negative root 3 over 2, negative 1/2. So our tangent here is going to be another positive 1 over root 3 or positive root 3 over 3. So then we just have to find the negative solution as well because we have plus or minus root 3 over 3. So now we're looking for places where tangent is negative root 3 over 3. And it just so happens that that would be where the x value is negative root 3 over 2 and the y value is 1/2, which is at 5 pi over 6. And then following that across the unit circle here, at 11 pi over 6, we also have the coordinate root 3 over 2, negative 1/2. And so that's also going to give us a tangent value of negative root 3 over 3. So all 4 of these will be solutions to 3 tangent squared theta equals 1. So our solutions will be theta equals pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay. Any questions with that one? any numbers we're not sure where they came from, anything like that. Okay, so for tangent in particular, once you figure out like a combination of x and y values that give you the tangent that you're looking for, they're a lot easier to spot around the unit circle. Okay, so those are kind of the two a little bit more simple cases where you end up getting down to like one trig function equals something, and you have to try and then find what values of theta that works for. The other kind that we're going to look at now is where you might have to do a little bit more, like with factoring, or you might have to set multiple things equal to 0 or something, and then solve those equations and end up with potentially more solutions here. So that's what we're going to take a look at next. So third example, stay. This time we've got cosine of x minus 2 sine cosine of x equals 0. And we want our solutions from 0 to 2 pi. All right. So for this one, we might think that, subtracting or adding, 2 sine cosine x to both sides and then canceling a cosine would be good. And that will get you at least one solution, but the problem is we could be ignoring potential solutions here. And we don't want to do that. So instead, what I would try here is factoring first. Because anytime you cancel like a sine or a cosine or something like that on either side, sometimes that can end up ignoring possible solutions. So the first thing we want to do, notice how there's a cosine in both of these. So I'm going to factor that out because that's the greatest common factor. So we get cosine of x times 1 minus 2 sine x equals 0. And then once I've done that, I can go and set these each individually equal to 0. So we can go cosine of x equals 0 and 1 minus 2 sine of x equals 0. And then solve those separately, and anything we get as a solution will be a solution to the problem overall. It's kind of like when you guys did factoring and were finding zeros and stuff like that. Actually, it's exactly like that. When you would factor something and then you would set both parts equal to 0. This is exactly what we're doing here, just with the added fun of trig. So now we're looking for places between 0 and 2 pi where cosine is 0. So now we're thinking the unit circle. And we know that cosine is x. So we've got two places where cosine is 0. We have it at pi over 2 and at 3 pi over 2. So we can start kind of collecting things that will work there. And now we want to also solve this one. So I might add 2 sine x to both sides. And then divide both sides by 2 to get 1/2 equals sine of x. And then we're back to that first example, actually, where we set sine of x equal to 1/2. And we came up with two solutions there. We had pi over 6 and 5 pi over 6. So that brings us back to example 1, where we set sine of x equal to 1/2. And so all four of these things that we have found are solutions. So we have x equals pi over 2, 3 pi over 2, pi over 6 and 5 pi over 6 for our solution to the whole thing. Okay. Any questions from that one? Any numbers we're not sure where they came from? Okay. We're going to do one more, and the last one that we're going to do looks kind of like this. It's the same idea. It's got factoring in it and stuff. Just a little bit more factoring, kind of like we did last week. Or, yeah, last week. So, example 4. We have 2 cosine squared minus cosine equals 1. And we're going to go from 0 to 2 pi. Okay. So for this one, the first thing I would do is get the whole thing equal to 0. So I'm going to move the 1 over. So I'm going to subtract 1 from both sides. So we get 2 cosine squared theta minus cosine theta minus 1 equals 0. And so this is the same kind of factoring problem we were working with before. But if you want to, this is the kind that you can go, okay, 2x squared minus x minus 1 and factor it this way since we're a little bit more familiar with this. And then transition it back by plugging in cosine for x. Or you can factor it just starting here and treat the cosine as if it's an x. Either way you want to do it is fine, but the first thing I would do is multiply 2 times -1 is -2. Then we're looking for things that multiply to -2 and add to -1, which would be -2 and +1. So then we rewrite it as 2x squared minus 2x plus 1x minus 1. Split it down the middle, take out the greatest common factor. We get 2x times x minus 1 plus x minus 1. Since our GCF on this side was 1. Then we take out the x minus 1, and we're left with x minus 1 times 2x plus 1. So putting this back in terms of cosine over here, we have cosine theta minus 1 and 2 cosine theta plus 1 equals 0. So now we've factored it. And now we're exactly where we were in example 3, where we have to split it now and set each part individually equal to 0. So we have to go cosine minus 1 equals 0, and 2 cosine plus 1 equals 0. And then we solve them each individually. So we're looking for the place where cosine theta equals 1 for this one. And then the place where cosine theta equals -1/2 for this one, because we'd subtract 1 from both sides and then divide by 2 on both sides. So that's where we jump to the unit circle again. Since we're looking for 0 to 2 pi, we know cosine is 1 at 0 and pi. So that's our solution for the first part. And then for the second part, when cosine is -1/2, we know there's going to be 2 locations, one in the second quadrant and one in the third. And so we're looking for places where the x-coordinate is -1/2. That happens to be at 2 pi over 3, because that's the coordinate -1/2 √3/2. And then also at 4 pi over 3, because that's also the coordinate -1/2 and then -√3/2. So for this one, theta is 2 pi thirds and 4 pi thirds. And then these would all four be solutions to this equation. So our final answer, theta equals 0, pi, 2 pi thirds, and 4 pi thirds. Okay. Anything from that one that we have questions on? Anything we're not sure where it came from? Okay. Well then, I'm going to have you guys try a couple, and then we'll get the assignment for today. First one. We'll do cosine theta equals 1/2 on the interval 0 to pi. And we'll do oh, that one's a little harder than I intended. We'll do tangent squared minus 3 equals 0. Go ahead and try those two. When you think you've got them, type "got it" in the chat, and then we'll talk about them. Oh, and then this one will be solutions from 0 to 2 pi. All right, Jasmine's got it. For the first one, you're on the right track. If you've got one solution, that one solution should be pi over 3. On the second one, you're on the right track. If you've got tangent equals plus or minus root 3, then you're just looking for the places where tangent of theta is either positive or negative root 3. And if you figured out number 2, one more I'm going to give you. Tangent squared equals 3 minus 3 secant. And this one's a little bit harder, but I'll give you a hint. You're going to want to replace tangent squared using a Pythagorean identity. So think about it for a moment, and if we can't figure that out, then I will also finish off with that one. You should get 4 answers for number 2. One of them being pi over 3, and that's the first place that we see when we do tangent y over x, root 3 over 2 divided by 1/2. So you flip and multiply, and we get the 2's cancel again, we get just root 3 left. So that's when theta is pi over 3. And then we get that same xy combination in 4 other locations. The first one being at 2 pi over 3. where it's negative 1/2 and positive root 3 over 2, which gives us a tangent of negative root 3. Another one is down here at 4 pi over 3, where we have negative 1/2 negative root 3 over 2. And then lastly, at 5 pi over 3. Where we have the combination positive 1/2 negative root 3 over 2. So these would be our 4 solutions to number 2. All right, and then the last one. Has anyone figured out what I should replace tangent squared with? Anyone think they got it? All right, this one is a bit tough because it does require us to replace it with a Pythagorean identity. So remembering our Pythagorean identity, we have tangent squared plus 1 equals secant squared. Kind of off to the side, we know tangent squared plus 1 equals secant squared. So if I subtract 1 from both sides, we get tangent squared equals secant squared minus 1. So this I'm going to replace tangent squared with over here so that we have all one trig function that we're working with. Then I'm going to move everything over to one side. So we've got secant squared plus 3 secant minus 4, because I subtracted 3 over and I added 3 secant over, equals 0. And now this becomes just like the factoring one that we did for one of our examples. I think it was example 4. So now we can factor this thing. We're looking for things that multiply to negative 4 and add to 3. So that would be positive 4 and negative 1. So we get secant plus 4 times secant minus 1. And then we can set each of those. Oh, wait a minute. This problem doesn't work out nice. That's good. No, but it would work out nicely if this was negative, I believe. So just kidding. We're going to add 3 and get 2. And then we want things that multiply to 2 and add to 3, which would be 2 and 1. So then secant plus 2 and secant plus 1. That works out a little bit nicer. Sorry, I wrote down I incorrectly multiplied my head. That's what you get when you do that. Okay. So secant plus 2, secant plus 1, then we can set those separately equal to 0. Okay. So then we get that we're looking for places where secant is negative 2 or where secant is negative 1. And secant is 1 over cosine. So it's like if you were to take cosine and flip it. So we're also then looking for, if we want to think of it in terms of something that we know from the unit circle, we're looking for places where cosine of theta is negative 1/2 or where cosine of theta is also -1 because -1 is its own reciprocal. So sorry, this one turned into more of an example than one for you guys to try on your own, but if you got through it on your own, great. So then looking for places where cosine is -1/2, it's all going to be on the left-hand side of the unit circle. In 2 places. At 2 pi over 3 and at 4 pi over 3. And the place where cosine is -1 is only at pi. Okay, so that's some of the different ways of solving trig equations. And so let's go ahead and we're going to look at the homework, get some practice with these. So let me post that real quick. In the meantime, on a scale of 1 to 5, I'm curious. 1 being I'm completely lost, 5 being this is actually pretty easy. What are we feeling? 3 being maybe I need just to practice these on my own. Where are we at? Okay. Looks like we're mostly in the 3 and 4 range. The scattered 2 here and there. All right. So I'm going to go ahead and post the assignment, and then those of you who want to go over more of them with me can, and those of you who want to start trying to figure these out on your own, you're welcome to do that. So the assignment for today is a worksheet. Notice only page 1 of the worksheet is assigned. You can do page 2 if you would like extra practice, but page 2 is not required. So page 1, we're solving on the interval 0 to 2 pi for all the first 8 of these. And we have a good mix of type of problem, whether they involve factoring or not. And then we've got these last 3 are just solving for the variable on the interval they give you. So sometimes it's 0 to 2 pi or something like that, and sometimes it's 0 to 8 pi. And then page 2, if you would like to, the answers though are all written down here, so you can check your work. There's 25 of them. Feel free to do any of these that you want to for extra practice, but the homework is these 11. Okay, so at this point, you guys are free to go if you would like to start working on your own, or you can stick around if you want more examples. Other than that, have a good one. See you tomorrow.